This is a USB-C cable, and you probably have some of them laying around as well, because the USB-C connector is nowadays widely popular when it comes to connecting electrical devices. With it, you can not only charge things up, you can also transfer data as well as video and audio signals. Doing all of that with just one cable is pretty awesome, and I'm a big fan. But that does not mean that everything is perfect. For example, in a previous video I built this 100-watt power bank that, like the name implies, can output close to 100 watts of power through a USB-C cable, which can be used to power bigger devices. And there are already plans in place to increase this output power even more, up to 240 watts, which is enough to, for example, power a full-sized fridge. But as you might know, with great power comes great responsibility. And by that I mean, if you mishandle a wire with too much current, then things can get pretty hot and dangerous. Of course, this test setup was a bit exaggerated, but a badly made USB-C cable can come with a bigger resistance, meaning it will produce more power losses in the form of heat. I actually noticed such a problem while testing my 100-watt power bank, and that is why I ordered myself 13 USB-C cables from all sorts of popular and not so popular brands, which I will properly test in this video, to find out how much a bad USB-C cable can mess up your charging experience. Let's get started! This video is sponsored by Keysight's RF Back to Basics Bootcamp. So if you're like me and think that radio frequency is black magic, then this fundamentals course for RF engineering is for you. This free 3-part bootcamp covers the basics of RF signal chains and network analysis, signal analysis, and signal generation and modulation. If you're curious, then click the link below and get started right away. To start off, let me clarify that while choosing all my 13 USB-C cables, I didn't care at all about how fast they can transfer data or audio and video signals. I only cared about their power rating, and nowadays there appear to exist either 60-watt cables or 100-watt cables. Now you might be asking yourself, since cables are basically just copper wires, why can we not draw 100 watts, aka 5 amps at 20 volts, with a 60-watt cable, which normally only does a maximum of 3 amps at 20 volts. Well, first off, you're correct to think that a copper wire cannot limit the current flowing through it by itself, unless it is very thin and thus acts like a fuse. But instead, the cable comes with a so-called e-marker chip that lots of USB-C cable product descriptions love to mention. And this chip sits very close to the actual USB-C connector, like seen here. What it does is basically communicating with the power source and/or device and telling them that it can handle 5 amps at 20 volts, so 100 watts, which the power supply then happily offers. But if the cable does not come with such an e-marker chip, like every 60-watt cable out there, then the power supply only delivers just above 3 amps before turning off its outputs. At least in theory, because while doing tests later on, I actually tricked the power supply to output 100 watts of power through a 60-watt cable. I did this by using such a USB tester, which, like the name implies, can not only test your cable and power supply features, but also measures the most important electrical values. Very useful stuff. But anyway, by using a 100-watt cable on the input and a 60-watt cable on the output of the tester, you can trick the power supply to output 100 watts without a problem. And the last thing I would like to mention about those e-marker chips is that they are often advertised in a way to suggest that they somehow stabilize the noisy and unregulated output voltage of the power supply. But by doing a quick test with my oscilloscope, you can see that the noise level before and after the cable is about the same. So I can assure you that all the e-marker chip can do is telling the power supply what voltage and max current to output, nothing more. Okay, with that out of the way, we should have a basic understanding of how these two wire types differ from one another. But the question is now, what cable I ordered comes with the lowest resistance. This is important because the resistance directly determines how much voltage gets lost across the cable, and how much power of the original 100 watt from the power supply gets converted into useless heat through the cable. Of course, to keep the resistance low, you could use very thick wire or real high quality solder connections and connectors. But for such cables, you also need to keep the price point in mind. So I'm curious to find out how those manufacturers struck a good balance. So for my resistance test, I used, like previously shown, a 100 watt power supply in combination with a USB tester to mainly see the flowing current, a USB-C PD trigger boards to select the 20 volt rail, and a constant load to actually draw 100 watts of power. And to precisely measure the voltage before and after the cable, I used my Keysight multimeter that comes with lots of digits. Sadly though, directly measuring at the USB-C port was not possible, but I tried getting as close as possible to it during all measurements. And with that being said, I tested out all 13 cables at 100 watts, while writing down the current flow and the voltage before and after the cable to later calculate the voltage drop. And while doing so, I quickly discovered the worst performing cable, which was this USB-A to USB-C one that supposedly even works with 6 amps, so 120 watts, because it is using some special Xiaomi charger standard. I noticed it because it simply got hot during testing and even reached an outer temperature of above 40 degrees Celsius. Crazy. But I guess if you want a seat warmer that can also charge your phone, then this cable is for you. And as it turns out, it comes with a total resistance of 430 milliohm, which does not sound like a lot, but at a current draw of 5 amps, that equals a power loss of 11 watts, aka 11% of the 100 watts we started with. That is insane. I mean, with this excess power, you could, for example, slowly charge up a second phone. But anyway, the good news here is that all the other cables didn't feature such a temperature rise. So at first sight, they all seemed acceptable. Until at least I filled out my Excel chart with the measurements and created this beautiful graph. There you can see all the resistances of my tested cables, along with the power loss they create at 100 watts. And for me most surprising was that known big brand cables like Anker, that also produce great power banks, do feature a higher resistance and thus power loss in comparison to other probably smaller brands that I never heard of. And according to my graph, you would probably also think that this cable here won the comparison. But it definitely got a big advantage because it is only 30 cm long. And as you might know, the longer a wire, the bigger its resistance will be. So if we do a bit of math and convert all the milliohm values into milliohm per meter values, then you will quickly realize that this cable is not the best one, but instead one over here. And if we add the price tag now, then you might think that we got some good options here. But there is one last thing we have to keep in mind, and that is the official USB Type-C cable and connector specification document. There we can find out that there are no specifications for wire gauges, but instead just references, meaning every manufacturer can decide on their own how thick their power wires will be, or whether they use one or two of them. But what is obligatory is the voltage drop, which they define with a maximum of 500 millivolts, including the cable resistance and the contact resistance of the connector. So if we check back on the measurements and deduct a bit for measuring errors, then we can see that at best only 5 of the 13 cables pass this requirement, which is shocking. At this point, I was not even sure whether the cables were too old to meet these new specifications, or whether I misunderstood something or measured completely incorrectly, because these results are certainly not favorable, and I can't really crown a winner, because there is no superior cable among them. But please don't be scared or anything to use your USB-C cables at home now, because even in the worst case they only heat up a little bit. And luckily this will not get worse in the future, because the new standards will only increase the voltage and not the current, which is mainly responsible for the power losses. And with that being said, I hope you enjoyed this video and learned a thing or two. If so, consider supporting me through Patreon to keep the show going. Don't forget to like, share, subscribe and hit the notification bell. Stay creative, and I will see you next time!